And we are live. Welcome to the Node Guardians YouTube channel, where we discuss all things blockchain, decentralized web, smart contract programming, and cryptography, and much more. On this channel, you should expect podcasts like this one, but also code reviews, debates, and governance calls. I'm Sam, today hosting these episodes alongside Kayleen. We're both from Node Guardians, and our first guest today is Barnabé Monnot, a research scientist within the Robust Incentives Group at the Ethereum Foundation. Barnabé, thank you so much for joining us.
Thank you, Sam.
I guess that it would make sense to start with a little bit of an introduction about yourself. What is it that you do at the Ethereum Foundation? And then we can explore Ethereum's roadmap, as this is one of the main topics of this episode.
Nice. So hi, everyone. Thanks for having me here. It's been 3 years now that I'm at the Ethereum Foundation. I work at the Robust Incentives Group, which is a research team at the foundation that's very dedicated to economic mechanisms, game theory, anything that touches the way dApps think about their economics, the way the protocol thinks about economics, the way we upgrade the protocol to make Ethereum more secure and more sustainable. So we have all these works to check that.
Okay, so robust incentives mean that you have to work on the design of these components that you add to Ethereum or these components that you edit on Ethereum and make sure that these modifications are done in a sustainable way from a game theory perspective, but also from a technical perspective. Am I right?
Yeah, that's correct. So the game theory part is definitely important because in decentralized systems, it's trustless, right? So you don't know the person you have in front of you. You need to coordinate like this very large set of anonymous players. And so the game theory is very hard in that case. And then the technical part is, I would say, we do like give inputs on that. Of course, the developers are more responsible for getting these upgrades in the core client code. But yeah, it's deeply intertwined, the two of them together.
All right. I propose that we start demystifying Ethereum's roadmap from the scaling side of things, but also how to achieve this scalability while remaining decently decentralized and many other things. We've been hearing a lot about the merge, the verge, the surge, the purge, the scorch, the splurge. I've seen a few infographics on Twitter, a little bit on some other forums. These words have basically been like debated, discussed among many communities within the Ethereum ecosystem. So could you just define us at a high level, what are these and how they change Ethereum, how they're improving its scalability? Could you cast some light on these?
Sure. So these words, they come, like, as you said, from this infographic that Vitalik updates every year and puts on Twitter. So they refer to several streams of work, but at a high level, and that's my reading again, but two of the perspective is one is scaling. So just making the Ethereum base layer and the rollups, the whole layers that are built on Ethereum, just be able to accommodate more transactions, accommodate more user interactions. So scaling is one very important stream. And then maybe another way to think about the other updates is hardening. So making what we currently have more robust, more efficient, more secure. So you have things like single slot finality to make the consensus achieve economic finality faster. You have things like thinking about what does the cryptography we use look like in a post-quantum environment, things like ZK EVM. If we have a very good one, maybe we can enshrine that in the protocol. So just taking the components we already have, but make them more future-proof and more efficient.
All right. So what you've listed, all these improvements, whether it is account abstraction from a UX perspective, also you mentioned hardening, scalability, they are the functions that are added by the merge, the surge, the verge, the scourge, etc. Right?
Yes. Right? Yeah. Correct. Yeah.
And so we've been hearing a lot about sharding when it comes to scaling Ethereum. I will stick to the scaling side of things. And when I first heard about it, back in 2018 or 19, I was seeing some keynotes about scaling Ethereum by Vlad Zamfir at HCC 4 years ago or 3 years ago. I was seeing some propositions to evolve towards sharded architecture, but it feels like today's approach to sharding on Ethereum with Danksharding is slightly different than what was projected a few years ago. And so could you explain us the role of these shards? What are the shards in Danksharding, basically the rollups, and will shards eventually process storing, execution, and handling transactions in the future? What will this bring to Ethereum concretely, and how this notion of sharding has evolved? Why?
Yeah, that's a very good question. So I came in actually at the start of 2020 when I think there was still like this idea of execution shards, but then recently after Vitalik posted this rollup centric roadmap approach. So this whole like scalability stream, it's what we know as the surge, like the idea of providing more scale for rollups. So the idea was really that when you build in execution shards into the protocol, like there's a lot of questions on how these shards communicate with one another, on the execution models inside the different shards. So that was the plans before, let's say, 2020. And it means that you have to commit to specific decisions or designs early on. One advantage to moving to this rollup centric approach, or what we call data sharding, is that now we say, okay, at the base layer, we're not providing like these extra shards of execution. We're letting these rollups, which are secured by Ethereum, which inherit the Ethereum security, make these decisions on what their execution models are, how they deal with their cross-chain, like rollup to base layer, but also rollup to rollup communication. So we, at the base layer, we simply need to provide this resource, which is known as data availability, which is, let's say, the raw material that rollups need to consume to secure themselves with Ethereum. So yeah, we moved from this model where you have many execution shards in parallel to a model where the base layer is just trying to provide this big amount of data availability, different from data storage. So availability really means that the base layer needs to ensure that all this data is published once, and you can do that in ways that are very scalable. So one question I think you had was, is it still sharding? Like, and we talk about Danksharding, and sharding is in the name. And so it's not exactly sharding in the sense of you have like these parallel blockchains going on in parallel, but it's sharding in the sense that most, or let's say all nodes on the network, there's no one node that needs to store like the entire data. So the data availability that the base layer provides is kind of split between these different full nodes and light nodes that are playing these games to try to understand if all of the data set is available across the set of full nodes. So yeah, so it's sharding in that sense that things are split across many different nodes, and no one node needs to hold the entire data.
Okay, and we hear more currently, people speaking about proto-danksharding. That's right.
So yeah, I can talk a bit about Protodanksharding. So Danksharding is quite complex. So you have to think deeply about the network structure of how these sharded data availability samples, where they live, how the nodes kind of ping one another to understand if they are available. So that's definitely like a big research project. There's been a lot of progress on that. So the idea of Protodanksharding is to be able to scale already before we get to that very fancy data availability sampling engine, which is Danksharding. So Protodanksharding, yeah, trying to increase the data availability processing capabilities of the base layer today simply by creating bigger blocks, but separating the data availability resource from the execution resource.
So for the scalability aspect, a lot of features that are being introduced is sharding or proposer builder separation, or other like rollups and data availability. So going into the proposer builder separation aspect, could you give us a introduction of how this enables the separation between the validators and the builders to achieve scalability without sacrificing security or decentralization? And also, could you explain why this is needed?
Yeah, so proposer builder separation is more like a design philosophy. So it's the idea that during the block construction phase, the validator can delegate parts of block construction to another entity, which is called a builder. So today we often hear people asking, okay, when is proposer builder separation happening? They refer often to the idea that proposer builder separation is enshrined into the protocol. But if you look at how blocks are constructed today, we already have some kind of proposer builder separation, which is known as MEV Boost. So it's an out-of-protocol market for proposers to receive blocks that are made by third-party entities known as the builders. And so it could help with scaling in the sense that since block construction is expensive, like you need to think deeply about the economics, optimizing the packing of the transactions, possibly extracting MEV. Builders, you think of them as maybe more centralized entities, but entities that have much more powerful hardware or much more intelligence and sophistication in the way that they do things. And so since that block construction is kind of one shot, like you only need to build the block once, you let the builder make a very good block, possibly a large block in the case of Danksharding. So it's a block that would be made of data availability samples. So the builder does that, and then the rest of the network can verify very easily that either the block is EVM execution valid in the case of execution block, or that the samples are available in the case of data availability sampling. So it's really exploiting this asymmetry between the cost of block construction and the cost of block verification.
Yeah, thank you for the introduction. I have a very naive question regarding this proposer builder separation. So you said that builders could be centralized in the way that they propose these blocks to the proposers. What if builders censor transactions that they don't want to include to the proposer? Or what sort of prevents these proposers from choosing a same builder multiple times within this structure?
Right. Yeah. So that's also a very relevant question that we're definitely thinking deeply about. So one of the opportunities of delegating is that the person you're delegating to might do a better job, but one of the risks is that person might not have the same preference as you have. So maybe me as a proposer, I don't care about censoring transactions. I'm happy to let everyone into my block as long as they pay the base fee. But the builder might have competing incentives. If they are more sophisticated, if they invest more into hardware, they might be more visible. So there's maybe more reputation costs or legal reasons why they might not want to do certain things. And so in that case, yeah, as you say, one of the risks is censorship. One of the risks is exploitation of order flow, these different things. So on that front, there are ways to reintroduce parts of proposer input into the block construction. So you could build in these protocol mechanisms where the proposer is able to say, okay, you build a block for me, but it has to have like these things that I really care about. And the builder could say, okay, I don't want to build that block, so I'm going to pass on that opportunity, and maybe later on we can build a block together if you don't have like conflicting things that you want to ask me. It's still a trade-off, right? So what we see today with censorship and what it has kind of revealed is that we might be in a world where the person who's best able to build the block, and best in really like a pure economic sense, how much value the block returns to the proposer. So a person who's best able to build the block might be someone who wants to censor certain transactions. And so then there's always going to be a bit of a trade-off between how much value your block contains and how much censorship resistance it has. So that's definitely an important question.
And how does this come into play for resisting cross-domain MEV or centralized block production?
I don't know that we can resist cross-domain MEV because it's going to happen. It doesn't have value on both sides for builders to make these arbitrages, for instance. So cross-domain MEV is interesting because let's say you want to do cross-domain MEV between the Ethereum base layer and the rollups. It's going to be different from doing this extraction between Ethereum and things like Cosmos. So it really depends on the two domains that are on either side. But having something like PBS might actually make it a little easier for builders who are active on both domains to kind of coordinate their actions on both sides. And it's not necessarily a bad thing. So cross-domain MEV, as long as it looks like equilibrating the prices of DEXs on both sides, like it provides more market efficiency. So it can lead to more centralization pressure from the fact that there's network effects to being the builder that sits in the middle of all of these domains, but it might also unlock a bit more economic efficiency. So yeah, these are things that needs to be traded with one another.
So when you're explaining the basic mechanism and the function of PBS, you mentioned Danksharding and also MEV as well. And I was wondering if you could also sort of re-explain why proposer builder separation is necessary for Danksharding to remain decentralized.
Yes. So in Danksharding, the idea is that every block, so every 12 seconds, up to 32 megabytes, but on average 16 megabytes of data is provided by the network, by the Ethereum base layer as a whole. You can't do that on a consumer internet. So if it's your turn to propose the block, you're a bonded validator in Ethereum proof of stake. You have with Danksharding the opportunity to make a block that contains up to, let's say, 32 megabytes of data, but disseminating that block over the Gossip network or over the DHT that supports Danksharding, it's not going to be possible on just consumer grade internet. And so in that case, if you're a bonded validator, you can tell a builder who would invest in much better internet because they would be basically paid for that. Then the builder would be able to make that big block on behalf of the validator who can't and disseminate the contents of that block over the network. And so proposer builder separation, either in or out of protocol, is really what unlocks the design of Danksharding.
So it basically forces high system like requirement validators to get involved. And that allows us to break out of the specs that you have in order to get involved with Ethereum as a network, right?
Correct, yeah. So builders don't even need to be validators themselves. So that's a bit of a, let's say, pending design decision, like whether builders are bonded to the Ethereum proof of stake protocol. But yeah, indeed, they can break away from like the minimal requirements that we have for full nodes.
I would like now to explore this concept of data availability and also rollups. So getting back to seeing charts and infographics on Twitter, there's also another that's pretty notorious that likes to compare Ethereum data availability with its potential post-Danksharding and the potential of alternative data availability solutions that we might eventually explore later in that podcast. And so as Ethereum now is relying more on rollups and data availability for scaling, how are the gas fees calculated for all the data publication costs and like currently CALLDATA that is posted from these rollups to the mainnet? And how do you effectively plan to reduce the cost of publishing this data on the mainnet?
Yeah, so today the CALLDATA is counted as part of gas. So we only have one unit of resource, which is gas. CALLDATA is, let's say, the data that is posted by the transaction, either like a function call and its arguments. So for a rollup, the rollup is taking in user transaction, making a batch, and posting the data of these transactions onto the base layer. It's counted very simply. A non-zero byte of CALLDATA costs 16 gas and a 0 byte costs 4 gas. And so if your rollup is posting a ton of data, let's say 1,000 bytes of data, it costs 16,000 gas. And that gas is really, yeah, it's counted as part of the total execution of the gas. And so the first step to making that cost lower is to move to this Protodanksharding. So in Protodanksharding, we have this thing that we call multi-dimensional EIP 1559. We effectively separate two markets. So one market for the general purpose gas, in which the CALLDATA was previously counted. But now with Protodanksharding, we separate out the CALLDATA into its own market. And so we say, these are different resources, execution and data. They behave differently. Like from a node's perspective, it's very different operationally to deal with the execution or to deal with the data. And so we let these two different resources find their market prices in these independent markets. And so now, as a rollup, when I want to publish my CALLDATA, I'm going to go to the CALLDATA market and pay for these publication costs there. And if the CALLDATA market is large enough, and we can definitely expand a lot more the capacity of the market when we separate out the CALLDATA from the general gas. So when the capacity increases, then the market price should be lower. And we've done like some empirical studies on how much rollups currently consume in terms of CALLDATA. And what we see is that they're still very far from the amount of capacity that would be provided initially with Protodanksharding. And so the costs of publishing CALLDATA would be much lower after Protodanksharding.
In relation to this, in terms of the aspects of the rollup congestion fees, so is this also related to that cost as well? What happens when there's a huge influx of users that are onboarded once the scalability aspects also scale up as well? And is the EIP 1559 that you mentioned, is this also related into how these congestion fees are calculated?
Yeah, that's correct in a sense. So rollups, you can really think of them as like, let's say, carbon copies of the Ethereum base layer. And so they have to deal with, okay, I have a bunch of users who are coming in. The rollup has maybe more capacity, but it still is capacity constraint. And so when you have like too many users coming to your rollup, you have to decide who gets in and who doesn't. And so at the rollup, you, especially rollups which are, let's say, Ethereum equivalent or rollups that use like GEF as their full nodes, they can inherit something like EIP 1559 that helps them deal with that congestion. And so when the user comes in, the rollup has to kind of quote a price. When the rollup is not full, when there's enough capacity for everyone, basically the price that the rollup wants to quote to the user is the price that eventually the rollup is going to pay in data publication costs. It might want to quote a little bit more to, let's say, remunerate full nodes that are expanding like physical resources, but that's the only two costs. Now, if your rollup is full, like if you have a ton of users, you might have something like EIP 1559 kick in to say, okay, you know, now there's a lot of competition to get into my rollup on my infrastructure. If you want to be included kind of first or ahead of the pack, like you need to pay at least this much, which is what EIP 1559 gives you as a primitive of the mechanism. And so by combining the congestion cost with the data publication cost, the rollup is able to make a quote to the user, and the user can say, you know, now it's too expensive, so I'll come back when EIP 1559 will be lower, and I only pay the data publication costs, or I'm okay with paying that price, and I'm getting in right now.
And how do shards come into play and solve problems that occur from this?
So the shards that would be on the base layer, they improve upon the data publication cost. And so as a user, let's say if you're separating the cost between congestion and data publication, that second part, the data publication cost, would be lower because of the shard. If that cost is lower, it means also that, you know, more users might want to join in, and then you might have more demand, so the congestion cost might increase again. But yeah, sharding just improves the capacity of the base layer to receive more data availability, and reduce the data availability cost.
So with all of these updates on the gas fees and all of the data publication costs, what do these updates mean for the user, for the developer, especially on the UX aspect? Like, is there a lot of changes to that? How should the developers know about all of these updates and what will happen?
Yeah, so developers, let's say on the base layer, things don't change that much for them. If you are a developer of a bridge, you might find it useful to look into these new transactions that are using that CALLDATA market to publish the data, because these transactions can also hold a bit of execution. For instance, if you're a ZK rollup, you can do atomic bridging using these new transaction formats. But if you're like, let's say, a more general dApp developer, yeah, on the base layer, things don't really change for you. On the rollup, you might find tiny differences. So some of the rollups claim like EVM equivalence. So in terms of gas cost, like the relative prices don't change. But what you might find is some resources might be more plentiful. For instance, because the rollup full nodes are expected to be able to process more data, and because the rollup gas limits are higher, like you might find that it's a space where you have more plentiful access to the full node resources like storage or execution. And so it might induce different patterns of programming where you still want to be as gas efficient as possible, but perhaps that efficiency is not as important as it would be on the base layer itself.
And it seems today that in order to have high performance on a blockchain. I carefully say this, of course, it comes down to how data can be propagated and how fast it can be processed. And so we see new designs coming up, like parallel executions on some more modern blockchains. And I was reading some article that was giving some kind of forecast of what data dissemination capability will look like on some alt L1s and Ethereum fast sharding. I remember that it was something in the order, it was about a few megabytes. And I was wanting to understand is it still a scale that fits global adoption? Let's say there is a new killer app that comes on Ethereum and that onboards hundreds of thousands of users, millions of users. I would be very curious to know if we would be ready to handle the activity of galore of users on that system, even though we've reached a certain level of maturity on Ethereum scaling roadmap. And that can bring us to how to fit and make the blockchain trilemma formula work, and how to ensure to have like high enough performances without compromising decentralization. But yeah, I would be very curious to pick your brain, to have your input on this. Are we ready for global adoption, even past all these technical updates that are in sight for Ethereum?
Yeah, that's a good question. So I think one way to think about it is to look at where the bottlenecks are. So on the base layer, like we're very clear on what these are. Like the gas limit is 30 million, target 15 million with EIP-155. Like we don't want to go beyond that because, as you say, you have this blockchain trilemma. You increase the scale of the base layer, it means now your full nodes need to process more information, store more historical information, state accesses become costly. So yeah, you hurt decentralization when you do that. And so the aim, or let's say the target for global adoption, is really getting users to onboard onto more plentiful environments such as rollups. Today, there are still bottlenecks on the rollup. It would be hard for me to say if any rollup is able to accommodate a million users, but we definitely have much more room to improve upon the scale that they can accommodate. So rollups are still limited by just like full node capabilities. Like you can have super powerful computers running Geth that might be enough to give you a bit more scaling, but then you still need to publish that data. So the more transactions you're processing, the more data you're publishing to the base layer. So all these updates at the base layer to provide more DA, they really come in for making this cost as low as possible. And there's like ballpark numbers that are sometimes thrown around where you, when you think about Danksharding or when you think about Protodanksharding, but really the aim is to get to like sub-cent publication costs for data. And by sub-cent, we really mean like a thousandth of a cent, or like very, very tiny amounts so that it's practicable. That's one thing. And then another thing is, yeah, you can maybe be smarter. So you have like these different rollups that live in parallel. Maybe you don't send all of your million users to the same rollup. Like maybe they go, this million users, some of them, they want to play games, some of them, they want to be engaging in like DeFi or certain things. So you could have like different places where these different users come in. Sometimes they do need to communicate with one another. Let's say in the game that I'm playing, I earn a very valuable in-game item, and now I want to go and trade it on another rollup where you have this decentralized marketplace or something. Now I need to send that message or to send that trade across one rollup to another. And so, yeah, so the idea of scaling in that parallel approach is that it's not like an n square complexity where if you have n users, they all have to send one another messages like across the rollups. No, most of the activity is kind of contained in each rollup, but then sometimes you have these bridges that need to be used by the users to bridge information from one rollup to the next, and that's much more scalable as an approach. So it's really what we're aiming towards in terms of onboarding a million or a billion new users to the Ethereum ecosystem.
You mentioned the blockchain trilemma. So the question I have is, after the merge and the change to proof of stake, regarding decentralization, security, or scalability, how might there still exist centralization risks? So after being changed to proof of stake, what if the liquid staking model leads to a centralization as a few large providers sort of manage these large amounts of staked ETH? Like what would happen then?
Yeah, that's a good question. So one centralization pressure that kind of came in after the merge, but maybe was a bit underlying before that, is, as we discussed, proposer builder separation. So now the idea that because you have proof of stake, because you have solo validators in the system, because you need to have a system where the whole block is sort of outsourced to a builder, you can have centralization at that level. So it's both expected in the sense that the builder layer is centralized by definition or functionally due to the fact that they're sophisticated, but that's definitely a pressure that we are mindful of and we want to backstop as much as possible. And then you have other, let's say, pressures, as you mentioned, so things like liquid staking that got very popular post-merge. So POS is you're staking assets, like it's really based on this economic security of the native asset securing its own kind of network. So in proof of work, you can have things that it's not exactly liquid staking, but you can have hash rate derivatives. You can have complex financial products that are built on like these physical resources that are securing the network. But it's true that in proof of stake, the link is much more direct between the asset itself and these complex derivatives that live on the execution layer of the platform itself. So yeah, so there's definitely like much more risk. Here again, it might be seen as opportunities in the sense that liquid staking does allow you to do more with your capital that's currently kind of stuck staking the chain. But it's, yeah, we do observe that it has very strong network effects in that, you know, if there's like many different liquid staking derivatives, it might be difficult to make them fungible with one another. When someone gets slashed, how is that socialized across like the set of people that are participating in that liquid staking? So yeah, we're pretty early. There are some players like Lido, for instance, which have accumulated like a lot of market share. Coinbase also now has a kind of derivative asset based on the staking. But we do see, I would say, more and more heterogeneity in the models of liquid staking. So you have things like Rocket Pool. Justin Drake has been thinking about cryptographic ways to make a solo validator liquid staking, which is something that's not currently possible. So yeah, the hope is that the market doesn't solidify around, let's say, one winner too early, and that we can still explore like more of these designs, which, yeah, maybe some of them have stronger robustness against centralization pressures for sure.
There is this DVT concept that I find quite interesting that's coming up, where they basically allow multiple validators to get involved in the in securing the Ethereum for once. I mean, that's also one solution to that problem, I reckon, when it to decentralization issue.
Yeah. So DVTs are quite nice also to, if you're a solo validator and you're trying to harden your system a bit, like you can basically have this consensus over the messages that you're signing, so you can get a bit of help across like different things. And there is in fact a proposal or a project called Diva that is blending both DVT technology and liquid staking. So it looks like Rocket Pool, but with an added DVT layer on top. And yeah, these are things that could improve decentralization in that they just bring in more players into the mix, so that there's no one systemic player in the middle that can topple the whole thing.
Okay, now I would like to take a look at Ethereum in the whole landscape of data availability solutions that are out there and all the different base layers. So we've been seeing different designs to build a rollup. I mean, you have Validium, you can have your data availability coming from a committee, from another L1, but also from Ethereum. And these choices will have implication on the security of. It seems that as data availability solutions, other players are also coming up, like Celestia or EigenLayer. And how would basically Ethereum stand out from such base layers? I believe there is the economical security, but I also believe that it stands out on other aspects. And I would be very curious to know what would be the core differences between using Ethereum as a DA solution and these new systems that are coming up.
Yes. So we can talk maybe through them one by one. So Celestia, first is, I would say the main difference with Ethereum is the Celestia base layer itself is reduced in the concerns that it has. So they're really trying to zero in on the core functions of the base layer with respect to the rollups, which is the base layer provides data availability first and also provides consensus or some kind of ordering over the rollups that are built on Celestia. What that means is on Ethereum, the rollups settle on Ethereum base layer. So that's where the smart contract bridges are. That's where the proofs are published. On Celestia, the rollups kind of settle on themselves. So they're known as sovereign rollups. They publish their data to the Celestia base layer. So the Celestia base layer is still kind of the arbiter of truth for this ordering and this rollup consensus. But when there are fraud proofs or easy proofs, the rollups look much more like L1s that delegate these functions of data availability and consensus to the Celestia base layer. So it's a little different. Ethereum does have, let's say, stronger security requirements in that sense. So when you roll up, like you have to pay the fees to the Ethereum base layer, you have to settle on Ethereum itself. There are designs such as the Celestiums, which are rollups, smart contract rollups on Ethereum that move their data availability to the Celestia base layer. So in a sense, now you're both tied to some extent to Ethereum in that you can have bridges to the Ethereum base layer, but your data availability guarantees are provided by the Celestia base layer. So yeah, these are very, I would say, different models. In my opinion, it's a bit early to tell, okay, how do these difference, what do they induce in terms of the market, or how do dApps think about deploying to one or to the other? But it's clear that they are not, these two designs are just like orthogonal from one another, and so that market differentiation can be interesting to look at. And then the second one, the second one was EigenLayer. So yeah, EigenLayer is by itself not a base layer. It's more a mechanism that allows middleware, so outside applications, to secure themselves using the Ethereum base layer stake. How it works is, if I'm a validator on Ethereum, and let's say the EigenLayer middleware that provides this data availability is called EigenDA. Like if I want to participate in EigenDA, if I want to be not just a validator on Ethereum, but also a node on the EigenDA network that is making these data availability sampling games, what I do is I restake. So I allow the EigenDA network to slash me on Ethereum. And so now, if I do something bad on EigenDA, whenever I exit my stake from the Ethereum base layer, I'm going to be slashed by the EigenDA middleware. And so, in a sense, if you feel, let's say, uncomfortable relying on the security of the Celestia validator set, which maybe can be very decentralized, but maybe doesn't satisfy some preference that you have, you could use the EigenDA data availability network instead, if you find that you trust more into the security of the Ethereum stake, restaked via the EigenLayer middleware. So yeah, so here again, it's like a different way of thinking about security. It can lower the costs because EigenDA will be outside of the Ethereum protocol. It could be more scalable depending on how much of the data the restake validators can provide. So yeah, costs on Celestia and EigenLayer may be lower than the Ethereum network.
You mentioned that there are very different protocols compared to one another. So sort of based on these differences, what would be the significant factors that would drive a developer to choose Ethereum over other network protocols?
Yeah, that's a good question too. So again, it's hard to tell because some of these solutions are not live. In fact, none of these solutions pretty much are live. So we do have rollups on Ethereum, but we don't have like this whole data availability sampling layer that hyperscales the data availability capabilities. But let's say projecting into the future, first, I don't think it's a either or. Like I don't think you need to say, I just want to be on Ethereum. Like you see dApps launching on many different platforms. There's a market differentiation in the security that these dApps inherit. So if it's on Celestia, you have some security. You have the ability, for instance, on Celestia to use what is called like settlement rollups. So this design, you have a rollup on Celestia, which is home to many other rollups which are built on top. So depending on how that ecosystem is, you might find that there's a lot of liquidity that is shared between different rollups settling on the same settlement rollup. And so that might be a decision that drives where you want your dApp to land. But I do expect that the way you see, like brands opening up in different countries and they have kind of different ways of doing things based on the environment that they are, we could see like meaningful differences in the way that dApps interact or the way that they run their operations based on the different ecosystems that they would live in. Yeah, that's, I guess, a bit hand wavy, but it is, in my opinion, pretty hard to make these kinds of predictions correctly.
And scaling and data availability aside, there are also some other exciting updates that are on Ethereum's roadmap. One being account abstraction, and as the EIP 4337, we've seen what it basically enables developers and users to do on certain rollups that already have it in production. I can think of Starknet, but I believe that it is already it's also existing on ZK Sync or something like this. Could you explain us what is Ethereum's interpretation, account abstraction? What's going to be the first level of this function on Ethereum mainnet? And what does this mean for custody, user experience, for the end users, for the developers? Well, all things account abstraction on Ethereum, please, and when to expect it.
Sure. So on the Ethereum base layer, let's say today, all the transactions that users are making, they need to originate from what's called an externally owned account. So basically, an account on the Ethereum base layer that is backed by some private key that the user owns and that the user uses to sign the transaction. And then this transaction might be calling things like smart contracts. But the idea of account abstraction is to make the smart contracts a bit more first class. So to allow the user accounts themselves to have this extra intelligence that smart contracts have and make the transactions potentially from there. So there's been a lot of discussion around account abstraction in different proposals. So 2938, 3074. One of the, I would say, most discussed at the moment is known as ERC 4337. And if you pick out that term ERC, it's a kind of EIP that is trying to define a standard. And so what we're trying to do with ERC 4337 is define a standardized way that you might do this account abstraction in a way that you don't need to make protocol changes. And so that's a powerful approach. So things like 3074, they would need a hard fork to have this account abstraction into Ethereum. But ERC 4337 tries to go around that. So I'll go briefly into how it does it, because I think it's relevant to understand what it kind of unlocks. In ERC 4337, what the users send, instead of being transactions that are signed by their private key, so this EOA transaction, in ERC 4337, the user sends what's known as user operations. So they're kind of like non-executable transactions. They're more like intents that tell what they want to do, like a sort of recipe for what they want to do. So the user sends these user operations into what's known as an alt mempool. So you have a new mempool. You have one mempool for the user transaction, one mempool for the ERC 4337 user operations. And from that mempool, a third party known as the bundler takes a bunch of his user operations, packages them into what's known as a meta transaction, and then sends that meta transactions to be executed on the EVM, so on the Ethereum base layer virtual machine. And so now you go around this limitation that only externally owned accounts can send transactions by having the bundler send that transaction on behalf of the user. And so what's powerful here is that the user operation, it can be made more modular. So when you send a transaction, in a sense, two things happen. So there's validation and there's execution. So when I send my transaction as a user, the validation is the EVM checks that the signature that I have corresponds to the public key that is part of my account. So that's the 21,000 gas cost of a very basic transaction. With these user operations, you can move the validation logic to what is known as a smart contract wallet. So there's something deployed on Ethereum that is responsible for checking that the user operation satisfies some predicates that are very in advance. These predicates, they can be more general than an ECDSA signature. So for instance, they can be BLS signatures, which are nice because you can aggregate them. They can be post-quantum signatures, but they can also be things that are lighter touch. For instance, if you don't want the user ever to have to interact with private keys, public keys, etc., you can make on behalf of the user some kind of account on your dApp and use that account structure to validate that the user is indeed who they claim to be when they send that user operation. So validation is the first step. And once the transaction is validated, it can then be executed. And that's part of the meta transactions. And so that's a more flexible way to ensure ahead of time that the transaction is valid, and that can unlock different design patterns.
I was just like wondering the original like reason why this EIP was brought up in the first place. And is this EIP essentially for the benefit of the users rather than the network itself? Or does it also have benefits for the network?
Yeah, that's a good question. So maybe the benefits to the network are a bit more indirect. For instance, something that you can unlock more easily with account abstraction is things like smart contract wallets. So having the user not be responsible for custodying a private key, which is very hard, but making smart contract wallet more first-class actors of the protocol and allowing the user, for instance, if they lose access to their smart contract wallet from one way, there can be a system of guardians or some kind of multi-sig that allows them to recover parts of the keys or recover access to the wallet. And so definitely like a benefit to the user, like to have these, let's say, extra robustness in accessing their funds and a bit more intelligence in the way that the funds are custodied. It might flow out to the network as a whole, right? So the network is just made more secure by the fact that users are not losing their funds, that users are more confident in holding larger amounts of funds directly on-chain on these smart contract wallets. One thing that maybe needs to be said about ERC 4337 is that because it's out of protocol and because it uses like a fairly elegant way to do it, but still more operations than you would probably need if it was in protocol. Yeah, so ERC 457 might just have like more network costs. It incurs more operations, more checks. So just like the gas cost of a basic 4337 transaction, I think the minimum is evaluated at something like 42,000, which is already twice than the gas cost of the most basic regular transaction. So yeah, so because it's out of protocol, you might have a bit more load on the network to process these transactions, and then you need to have this alternative mempool, which is also like a separate thing. So yeah, but I would say overall probably positive for the network.
Are there any other EIPs that developers should look forward to?
Yep. Yeah. So sorry, I thought that was more to the question, but yeah, in my reading, the account abstraction definitely is the biggest user side change, like to the way user transactions or user intents or user actions are kind of dealt with. But there are two more changes that are, let's say, in the pipeline that eventually might have important consequences on the EVM itself and also on the way that developers think about interacting with the EVM. The first one is EOF, that's short for EVM object format. It's currently considered for inclusion. Like if you listen to the all core devs call, there's a lot of discussion at the moment on what is included into the next hard forks, because you need a hard fork to include that. But the idea of EOF is to provide some kind of versioning system for the EVM. And so you could have an upgrade path for the opcodes. You could have a way of deprecating opcodes that we don't want to support anymore. So that object format is pretty powerful to make the EVM a bit more, let's say, flexible in how it's interpreted. That might have ripple effects to developers who then have to understand what kind of EVM version they are targeting with their dApp and what makes sense, let's say, for their architecture. So that's the first one. And the second one is something that is part of the Verge on the roadmap of Ethereum, which is moving to the stateless Ethereum, where full nodes don't need to hold the whole state. That means that when a transaction is happening, it needs to come in to the node with a witness that tells what is the transaction touching, like the state accesses that it's going to make. It's very positive because state accesses currently really are the bottleneck to scaling the base layer more. It's just very costly to have a very large state that you need to access very frequently. And so with statelessness, you have a way of making essentially storage much cheaper, because when the storage is not being used, you don't need to think about it. And when it's being used, there's this extra cost of computing like this witness, but that cost can be managed by something like a builder or something like a state witness provider. And so when storage costs eventually decrease, it might incentivize dApp developers to change the way they think about storing data on the base layer.
All right. And any other, I believe this is very hard to change the legacy Ethereum in such a way, but are there any plans to make Ethereum compatible with other, high-level languages? I mean, languages in general, implementing other virtual machines. I believe this is quite challenging, and I'm not sure if I've seen this in the famous infographics about the Ethereum roadmap, but would that be something doable in the near future?
Yeah, that's a good question too. So there's really like a difference between when we say Ethereum today, we have to specify if we mean Ethereum base layer or Ethereum as like this system that is the base layer and the rollups. At the base layer, I would say the chances are pretty slim that we see another execution environment than the EVM. So when there was what we discussed early in this chat, this idea of multiple shards that were execution shards, at some point there was some ideas that some shards could have some kind of execution environment, some shards could have another. Maybe it's a bit like what Polkadot looks like today. I don't think this is going to be happening. What might happen at the base layer is moving to some kind of ZK EVM, so requiring that the execution on the base layer comes with a validity proof of that execution. I would be pretty surprised if we had an upgrade path with more execution environments. That's for the base layer. But then on the rollup layer, there's a lot more flexibility and a lot more design space for moving to different execution environments. We already see that today. So you have Fuel, which has its own Fuel VM, which relies on something a bit closer to the UTXO account model and way of doing things. Things like Starkware has Cairo and their VM that is maybe better able to create validity proofs of execution. So you do have a lot more flexibility on the rollup side to come up with new and maybe better customized execution environments to the applications that you expect on your infrastructure.
I guess you get all that feature exhaustivity through the rollups as they're kind of part of Ethereum's offering as a whole. So that really sets in a very interesting position for Ethereum in the future, as we also see new designs coming up like restaking, which is also a topic that we will explore this month on the channel. And I believe that this answer wraps up our first episode about Ethereum roadmap. Barnabé, thank you so much for your time. Really enjoyed hearing your perspective and your insights about what's planned. And if listeners want to stay in touch with you and follow your work, what's the best way to communicate, to contact you?
Yeah, I'm on Twitter at Barnabé Monnot. I'm on other networks that I'm currently exploring as well. I'm on cryptodon.lol and Farcaster. Yeah, I'm early into my social media exploration, but we also have a webpage for our robust incentive group. You can find it on GitHub if you type RIG. There's many ways. I think if you look for me, you will find me, or if you look for our team.
And if you look for us, I guess you're already there, but you are more than welcome to subscribe to our channel in order not to miss the next episodes. And you'll find in the description all the relevant links to engage with Barnabé. You might as well follow us on Twitter at Node Guardians, or visit our website where you can find some challenges to test out your Solidity skills, which would be more than happy to see you trying. Again, thank you very much, Barnabé. Thank you, Kaylin. Thank you, everyone, and see you very soon.